Hey Falcons, it's Miss Valeski here. In this segment, I'd like to talk to you about the relationship between intermolecular forces and temperature and how that creates the states of matter that we interact with in everyday life. So let's get started. Here you can see in the slide, we've got a molecule of water. Recall from this unit that water has a hydrogen bond, IMF, because of the hydrogen and oxygen and the unequal sharing of electrons. So the first scenario we're going to look at today is the same substance, so molecules of water, but we're going to change the temperature and see what that does to the molecules of water and how that creates different states of matter. So let's go ahead and place our water molecule into a chamber so that we can manipulate temperature and see what happens. Here you can see the chamber we're going to use, and let's assume all these small blue particles are the water molecules that we discussed. So we said that the IMF between water molecules is a hydrogen force. So let's go ahead and change the temperature, which is the average kinetic energy, or think of that as the speed that the water molecules are going. All right, let's take a look at the animation. So as we see here, we're raising the heat in the chamber. So we're starting to see the water molecules move a little bit faster. That overall average kinetic energy is increasing. Now we're not changing the substance. The IMF is still hydrogen bond, and that's attracting the water molecules to each other. However, as we increase that heat, we're starting to have molecules that actually can leave or break that IMF and leave as a gas. So as we continue to add more heat, there are more and more molecules that are able to disengage or break the IMF and leave as a gas. The IMF for each water molecule is still hydrogen, but again, because we now have more kinetic energy, we're able to disrupt more and more of the IMFs that were holding it together. We now see all of those IMFs broken. There's enough energy in here to allow water to become a gas. That's ultimately what boiling point is. It's when you can disrupt all of the IMFs of that particular substance. Now we're starting to cool the chamber. So we're starting to see the average kinetic energy, or think of that as the speed of the particles, starting to decrease. As the water molecules start to slow down, those IMFs are able to kind of re-engage. And again, the IMF hasn't changed, but with temperature, it's allowing those different IMFs to engage or to be disrupted based on what's happening. All right, let's take a look at now a second scenario. This one, we had the same substance, we had the same IMF, but we changed the kinetic energy. Now let's look at the opposite of that. Let's look at different substances at the same temperature. So now we're taking a look at this nature picture where we have solid, liquid, and gas. All of the things that you see in this picture, though, have different chemical formulas. And recall that the IMF is determined by the symmetry of that particular chemical compound. So different substances have different IMFs. The fact that they're at the same temperature tells us their average kinetic energy is the same. So again, we talked about this in class, thinking about the table, the water coming out of the faucet, and the oxygen in the classroom. So here, the same temperature means all these different substances have the same average kinetic energy. However, because their chemical formulas are different, they have different IMFs, which contribute to them being at different states of matter. Let's take a look at a specific example. So here we have two different chemical compounds. We have iodine monochloride and we have bromine gas. Let's say they're both at 0 degrees Celsius. They both have approximately the same molecular weight, and we can actually see that both of them are linear. But recall again that your iodine monochloride actually is going to be polar. The reason for this is the unequal sharing of electrons. So the chlorine actually is going to have those electrons, and we're going to see that molecules of iodine monochloride actually are going to have dipole-dipole IMF. Now let's take a look at the bromine at the bottom. You have, again, it's linear, but your difference in electronegativity is 0. So the electrons are being shared equally. This is nonpolar. Therefore, you would have a London dispersion force between molecules of bromine gas. So you have a stronger IMF in the molecule at the top, the iodine monochloride. So it would make sense that it's sticking more of those molecules together, attracting them together into a solid, whereas in bromine gas, you have a weaker IMF at the same temperature. Therefore, you have more of those molecules that can disrupt those IMFs into a liquid at that same average kinetic energy. In sum, we've got, again, our iodine monochloride with our dipole-dipole attractions. There's our London dispersion on our bromine gas. It's easier to break those weaker IMFs. Less energy and temperature would be needed to do so. And again, relating this back to boiling point, which we saw in the chamber, bromine gas would have a lower boiling point because its IMFs is weaker in comparison to iodine monochloride. So that's all I have for today, Falcons. Good luck and happy studying.